Okay, we are going to, well, this is the bonus. Please turn in if you have it.
What does it get bonus to? Like you
I just add it to something. Yeah. Okay, lots to do today. A lot to do. 7.2. We're moving on to a section called Volumes. This is a very geometric section. We did some geometric stuff last time because we had to graph things, right? Find areas between them. And there were basically two ways we approached it. We either looked at a top function, a bottom function, found the area between them, or we did sideways and did like left and right. Yes? Okay, so today I want to keep all that stuff on the back burner. We're going to need some of those concepts, but I'm going to start out with some geometry. So let's see if this is comfortable for everyone. We all know that the area of a rectangle is length times width, right? We all accept that as truth? Okay. The volume of a box, all right, now there's a technical name for a three-dimensional box like this. It's called a parallelepiped. But I'm not going to be sitting here saying parallelepiped. It's a box, all right? Solid box. All right, so we've got this solid box. The volume of it, length times width times height. You seen that before? Okay, I want you to notice something. If this is the width, this is the length, this is the height, then the volume is length times width times height is really just the area of that top rectangle, right, which would be width times length, times how deep it is, which is h. Same thing with a right cylinder. If you take a right cylinder, go look up the volume formula, it's pi r squared times h. Pi r squared should look familiar as being the area of a circle, right? So what you're doing is you're taking the area of this top piece and you're multiplying it times the height, which is almost like the depth of the cylinder, and that gives you the total volume, right? So this is twice that's happened. We have two solids. To find the volume, we take the area of one of the faces and then multiply by how deep it is. Do you see that? Okay. Let's look at this one. This is just a general solid. It's not a box. It's not a cylinder. It's just a general blob, three-dimensional. The volume of this should be something times how deep it is, right? The something up here, well, I don't know what it is because it's not a nice shape that I know, right? But do you notice that this up here could be looked at possibly as like the area between two curves, maybe? And then you multiply by the depth and you would get how deep it is. So there are ways that we've learned, last class specifically, on how to find the area of weird shaped things. And then if we multiply how deep it is, then we get the volume. All right. Another object that we're going to be interested in today is something like this, which is the same as a cylinder, except I've made it shorter. Okay, so I've made h smaller, so it looks more like this. We call this a disk. All right, this is a disk. The volume of a disk is still pi r squared times h. But what happens if we cut out an inside piece of this disk? So yeah, what we'll do is we look at it as like two disks, right? We have one big disk, which is going to be the one with the red radius, which I'm calling radius out, the outer radius. Whatever that outer radius is, pi times that radius squared times h would be the volume of the whole thing, right? Then we want to take out this smaller piece. So that's hollow inside. I can put my hand through there. So that the volume of that smaller one is the radius, the inner radius, I'm calling it inner radius, squared times pi times h. So whatever that volume is of the whole thing, take away, subtract the volume of the smaller piece inside, and that would give you the volume of that object, right? We call that a washer. And you understand why, right? You've seen a washer like bolts and nuts and washers, and washers are very thin usually, right? Oh yeah, there's that game. Yeah, my cousin loves that game. I don't like that game, yeah. I just suck at it, so. All right, so now this last picture, this is the same as this picture, I just turned it sideways. Just so everyone understands, it doesn't matter which way we orient this thing. If I'm trying to find the volume of this solid right here, then if I know how wide this is, right, then all I need to do is find that area. If I find that area, then I've got the volume of the whole thing. All right, that's what we're working with today, these basic geometric shapes. So let me see what else we got there. Okay, so please, if you could, turn your attention to the board, and I'd like to show you what today is about. So that's what we did last class. We have two functions, right? Bounded. We have an upper and a lower bound on that region. The region goes from A to B. Can you all see that? Mm-hmm. All right. What we want to do is turn my phone silent first. 10 points. Cost me 10 points. Just doesn't cost you 10 points.
No, we could get 10 points for our next exam, each one of us.
I'll have to make it hard then. I'll make the test harder to compensate for that. Okay. What we want to do is we want to imagine taking that region, which lives on a flat sheet of paper, right? We want to take that region, doesn't matter. And we don't want to find the area. That was last class. We want to imagine taking this and rotating it around the x-axis. So now instead of being on a flat sheet of paper, we want to look at this in three-dimensional space. If we rotate that around the x-axis, so I use this little curved arrow, which tells you I'm going around the x-axis, right? That's spinning it. Do you kind of get a mental image of what this would look like? Well, that's why I have the computer.
It's like you're making a paper towel song.
Like a what?
Like you're making a paper towel song.
Like a paper towel thing?
Yeah, it's a cylinder inside it.
Well, look at this over here. You see that? Isn't that cool? I've got this in three-dimensional space now. All right, so what we're going to do is we're going to take it and we want to take it and imagine rotating it around through three-dimensional space like that, right? And as I do that, I want to leave behind a copy of it. So it's going to look like this, right? And this is a solid. You agree?
That's pretty sweet.
It has a hole in it, but the hole is not like a straight hole, is it? Let me try and, see? Because the inside is kind of got a curve in it on the inside also, right? Do y'all see that?
Yeah.
Okay. What's the volume of that? That's the question. Can we find the volume of something like that? Okay. All right. Now, that's what we're going to do, and it's actually going to turn out to be not, hopefully for you, not as bad as it looks. Then imagine, I don't have a different program for this, but imagine instead that we had the other situation from last class, which was, where it was like that. Now, forget that it's x and y and a and b, but remember when we said it was sideways, you had to integrate with respect to y instead? Okay, so if we have a situation like that, we can still rotate that, but this time we would rotate around the y-axis and get a solid. In this case, it would be the same exact solid. But there's two basic concepts. If someone gives you an area, right, some region, we want to be able to rotate that around the x-axis and then possibly the y-axis. And then maybe we would just want to rotate it around some arbitrary line. Maybe it doesn't have to be the x or y-axis. But let's start with the most basic, which is around the x-axis. All right? Questions on what we're doing? Pardon me? We're going to come up with a formula. We're going to come up with a formula. You're going to help me do it. Okay? So let's try and do it in general first. Usually I give you an example first, then get the general formula, but I think y'all are capable of getting a general formula. So let's say that we're starting out with some function of x here, f, and then below it some function of x here, which I'm calling g. And we're going from a to b, all right? And I want to rotate this, we say, about the x-axis. That's the way we say it. The x-axis. So how did we find areas? What did we use to find areas? When I first introduced you to the idea of an area, I used what?
The formula, like the f minus g, the integral of f.
Yes, before that. What did we do to convince ourselves of areas? What? The Riemann sums, right?
Right.
Didn't the whole idea of the integral come from the idea of a Riemann sum? And I told you it was important to understand where this comes from because eventually we're going to need it again, and today's that day. So what I'm going to do is I'm going to take a look at an arbitrary rectangle that we would have used to find the area, right? That little slice right there, I'm going to imagine moving that slice over here. I'm just going to make kind of another copy of the x-axis and just have the rectangle here. On the top of that rectangle is the f function. On the bottom of that rectangle, right, is the g function. Nothing new from last class yet, right? If I take this one little piece, just that one little piece, and rotate it around the x-axis, what object would I get? A washer, wouldn't I? So let's imagine taking this. Let's draw a dotted line here to represent our axis of rotation. Okay, so I'm going to take that, and this is telling me I'm rotating it around the x-axis. Then I have a third picture over here of what that would look like, which would be, do you see this?
Yes.
It would look something like this. If you can't draw it that well, don't worry about it, okay? That's what that would look like rotated around, roughly, right? You got your axis of rotation is right in there. And you can even see the little rectangle in here. That's the rectangle right here that just got rotated around. Yeah? So you just told me a second ago, and we had it up here on the board, how to find the volume of a washer. What are the two things we need to know? Well, there's actually three things.
The area of the inner and outer radius.
The inner and outer radius, right? The outer radius and the inner radius.
The height.
And then the height. Okay, let's talk about those pieces. Let's start with the height. But I've turned it sideways, right? Instead of like this, right? It's turned sideways. So the height was this, right? What's the height for us? Dx, right? Wasn't dx the width of the rectangle?
Yeah.
Okay, so I know that this right here is dx. Then I need the radius, the inner radius and the outer radius. So let's talk about inner radius or outer radius. Which one do you want first?
Outer radius.
You want the outer? The outer radius is the distance from the center to any edge of this washer, right? So why don't I take it all the way up to the top edge? What is that distance?
Maybe 0 to the top of f.
It's 0 to the top of f. So isn't that just f?
Right.
That's just f. The function f of x. Isn't it? So what happens here is if I want to know distance from here to here, right? I'm going to draw it on this picture, actually. The distance from here to here would be f. Agreed?
Yes.
And as I move this around, right, if I move this sliver over to the side, that top will change, won't it? Which is why f is controlling it. F is a function of x, so as x changes, that height will change. Now what about the inner radius? That's g. And we said that the volume of this whole thing would be the volume of the outer cylinder minus the volume of the inner cylinder, wouldn't we? Wouldn't that be what we get? So let's look at what the volume of this is. The volume of this is, well, what's the volume of the big cylinder without anything taken out? Pi R out squared times H minus pi R in squared H, right? That's what we have? Okay, what is, I'm going to move this down here. What is the outer radius?
F.
F. So this is the function f squared. Understand? Times h. What's the h? Dx minus pi g squared times dx. That is the volume of one sliver, one washer of this thing rotated, yeah? And all we want to do now is add these up, all of them, an infinite number of them, which means we're going to bring in the summation, and then when we do an infinite number of them, the summation becomes the integral. Yes? So I just need the integral of this formula, right? And I'm there? Understand this? Okay, but there's a couple things we can do because this has some stuff in common. They both have pi, right? They both have dx. So I'm going to do it this way. Watch. Pi, I'm going to factor pi out. If I factor pi out, I'm left with f squared minus g squared. And then I'd need to factor out the dx also, right? But I'm going to put the dx on the back side. Because isn't that where it always appeared in the formula for the integral? Yeah. So I'm going to put dx back here. That's the volume of just that piece. So if we want the volume of the entire solid, yep, it'll be the integral from a to b, because that's where we're going to let x vary from, of this formula. Now pi is a constant, isn't it? So that can come out of the integral completely. Pi. I'm going to put a big V up here. And then it's just this formula. It's f squared. I'm going to write f of x squared minus g of x squared dx. That's it. That's the formula. So if you are given a function, or two curves, and they enclose a region, and these are both functions of x, and you want to rotate that around the x-axis, you need to be able to evaluate this integral right here.
Is that on formula sheet or?
Nope. Okay? That's it. But I'm going to make one tweak to this that's going to help us in a little while, all right? And that's this. This is pretty general, but the most general formula that I want to use is this. So this is my most general formula. Would look something like this. The volume will be pi integral a to b of the r out squared minus r in squared dx. Right? Now, and I have to change one more thing in order to make this the most general it can be. D question mark. And the reason why I'm going to say D question mark is because there might be a problem in a little while where our regions are functions of y, and we're rotating around this way. And so we're going to want to know, we're going to change our integration variable from x to y. So this right here will be x or it will be y. It'll just depend on the region itself. As far as the radius is concerned, you're always going to be looking to find an outer and inner radius. That's always going to be the issue. Okay? Questions? Okay. All right. You ready to do one? All right. Do you see a little bit now why the understanding the Riemann sum, just where it comes from, is important here? Yes?
So we're doing it just using y and x, we're not really using z? It's three-dimensional?
That's right. No, we don't need z at all.
Cool.
Yeah, we don't need z at all. Different class. Cal 3. All right. I want to do find volume of region bounded by y equals 1/4 x squared, y equals 5 minus x squared, if rotated about the x-axis. It's important in the problem that you understand which axis of what the axis of rotation is, because if this said y-axis, it would be a totally different problem. Our answer would be different. Let me show you a real quick picture of why it's important. And then we'll get back to this. Let's say we had this region right here. And I'm going to make this region very simple. You know what? I'll make it even easier. Okay, that right there. Let's say I had that little rectangular region. I said wrap that around the x-axis. Okay? It would look like this, right? And it would have some volume to it. What if I said wrap it around the y-axis? It would give you this, right? Totally different pictures, right? Totally different volumes. So when we're told here x-axis, we need to pay attention to it, right? Got it? Sometimes they're the same, but in general they're not. Sometimes they're the same volume, but in general they're not. Okay, so what do you think we're going to start with? A picture, right? We're going to have to start with a picture. So we have parabola 1/4 x squared. Looks like this. Y equals 1/4 x squared. And then 5 minus x squared is a parabola that opens down. It's got a y-intercept up here at 5. Opens down, so I'm thinking they hit each other somewhere, right? Everybody see the region? This region is what we want to wrap around the x-axis. Okay? Now, I'm going to need my intersection points, right? Would you like to get those now or later?
No.
You want to get them now? Okay. So how about the intersections? I didn't write down what this one was. It was 5 minus x squared. So I'm going to set those equal to each other. I'll multiply everything by 4 to clear the fractions. I'll move everything to one side, or sorry, I'll move just my x squareds to one side. I'll divide by 5, and I'll get plus or minus 2 for x. So I know right now that my integral is going to go from -2 to 2, right? Yes? Now I need to come up with the formula. Now, there's a temptation to just go right to that formula. Volume equals pi times outer radius squared, blah, blah, all that. If you want to save yourself from getting things wrong, which I think you do, I insist that you draw exactly what we drew when we were developing the formula, which means over here on the side, right next to this, I'm going to draw my x-axis. I'm going to show that this is my axis of rotation. I'm going to come in here and pick an arbitrary rectangle inside this region, and it's completely arbitrary. I can pick anything in here. I'm just going to pick this right here, all right? And then I'm going to kind of translate that over here and draw it on this side. Okay? We have the top of this rectangle is dictated by this parabola, yes? And the bottom of that rectangle, I'll do it in blue, is dictated by the other parabola. I need to determine what the outer and inner radius is. And that's always going to be the distance from the axis of rotation to the outer edge of the rectangle, is the outer radius, then the distance from the axis of rotation to the lower part, which is the inner radius. In this case, it's just that function and the other function, right? But later on, this axis of rotation is going to be moved around, so we need to be comfortable measuring that distance. So from here to here, we all know is which one of the parabolas. 5 minus x squared. Agreed? And then the inner radius is this distance, which is 1/4 x squared. And now we can go to the formula. And I'd like to point one more thing out, even though we're not going to need it for our formula. Again, this is because I know where we're going. The distance from the origin to the rectangle that I picked, right, to this rectangle, that distance is x, isn't it? Because x is going to change. I'm going to allow x to vary between -2 and 2. But that distance has no bearing on our volume, does it? As far as our formula for it? Okay, later it will. I think I'm ready. Are you ready for the formula? Okay, the volume will be what? Pi. Pi integral -2 to 2. Phi minus x squared is the outer radius, right? So phi minus x squared squared minus the inner radius, which was 1/4 x squared squared dx. It is not that. You have to FOIL that out, right? It is not that. You square the outer radius, you square the inner radius separately. Because these aren't the same things, are they? Right?
No.
These are not the same things. So just be careful, because when I'm grading these, the things I'm going to be looking for are your picture, your diagram, your setup of the integral. All parentheses have to be in the right place, squares have to be in the right place. I'm not going to ask you to evaluate these. You'll have a few that you'll have to evaluate, some area problems where you have to go all the way down to the answer. But this test will have a lot of problems where it's set up the integral, don't worry about evaluating it. But you got to set them up right. That will be the answer on a test, because we know what to do with this now, right? We would square that. That would be a polynomial. We'd raise that, and then we would take antiderivative, plug in all the numbers, and that's That's trivial at this point for us. Yeah. This setup's the most important thing. I'm not saying you can't do it, it's just I'm not going to do it here in class because I can't eat up another 10 minutes on each one of these doing that. Okay? All right, so equals and then dot, dot, dot. You do the rest. Understand? Good? Okay. Let's see what happens when we have a problem like this. How about, same thing, find the volume of the region. This is the region bounded by y equals natural log x, y equals 1, y equals 2, x equals 0, about the y-axis. Yes, y-axis, not x-axis. Let's start with a picture, all right? You must be able to generate a good picture, right? Or else things are going to go bad for you quick. I'm going to use some colored markers here. Let's start with y is the natural log of x. We all know that that looks like this. Y equals 1. Y equals 1. Vertical or horizontal? Horizontal line, y is 1. I know what's going to happen here. Let me slant this just a little bit more. Exaggerate this up. Okay. Y is 1 is here, let's say. Y is 1. Next one.
X is 0, so it's just the y-axis?
Y is 2.
Oh, y is 2.
Y is 2. Y is 2 is right here. And finally, I'm out of colors, so I'll use black. X is 0. Do you see the region bounded by all 4?
Yes.
Yes? Okay. Just this right here, right? And we are trying to rotate that where?
Around the y-axis.
Around the y-axis. Things are different now. This is like last class. If we were asked to find the area of this, right? We would want to do it with respect to which variable?